recording, we were talking about the size of determinations of the sedimentation tank. Actually, there were three major criteria we normally used to determine the size. The first one is the surface loading. Surface loadings, in fact, there are many terms calling the these factors. Actually, the surface loading is the the flow rates. Last week we were talking about the particles having settling velocities Vs, and the water get into the sedimentation tanks and overflowing to the tops of the tanks with the overflow velocities VO. For the optimum design, VO should be equal to Vs, so that the settling times will be equivalent to the detention time. So this is what we have been talking so far. And also the major factors influencing the efficiencies of the settling removal. It's the factors that influenced the settling efficiencies of the particles is the surface area, in which the surface areas also has the relationship with the flow rates. Q divided by the surface area, it's equal to the overflow rates. This sometimes we call the overflow rate. But in some textbook, they may recognize this term as the surface loading rate. And some may recognize this term as the surface overflow rate. Sometimes it is a surface loading rate. Sometimes they call it as the surface overflow rates. But anyway, they are all the same. They means the flow rates divided by the surface area. Last week, I explained it, the importance of the overflow rates. If you still remember, if we could actually lower the overflow rates, we could enhance the settling efficiencies. And the way to decreasing the overflow velocities or the overflow rate. Sometimes we also call the overflow velocities or the overflow rates. What we can do, we have to enlarge the surface area. So if we enlarge the surface areas, the overflow velocities or the overflow rates tend to decrease. I gave you two examples. The tank with the larger surface area like this, and the same tanks having the same volumes, but with this a smaller surface area like this. Which one would yield the better settling efficiencies? Of course, the one with the larger surface areas will produce a good settling efficiencies. So the first parameters we use to determine the size is the surface loading rate. So these are the criteria. The detention times real loading rate, and the last one is the solid loading rate. For the surface loading rate, so it's equal to the flow rates divided by the surface area. The units of the flow rates is cubic meters per hour. The surface areas is square meters. That is why this term, the units is cubic meters per square meters per hours. We prefer to define it like this because it shows how we obtain these values. Even though if you get rid of this one, it will come as the meters per hours. It's actually the units of the velocities, but we prefer to express this amount in terms of the cubic meters per square meters per hours like this. So this is a kind of the criteria. Value will be given. You can use the criteria for the design, or you can use these criteria for the operations and control. For the detention time, we have been talking about these parameters several times. The detention times, or sometimes we call the HRT, it's always equal to the volumes divided by the flow rates. The volumes is always given as the cubic meters, and the flow rate is cubic meters per hour, so it comes as the time. So talking about the last one is the VL loading rate. So what is VL loading rate? VL loading rate, as you look at the unit, you will know this comes from the flow rates divided by wear length. So what is wear length? If you really take a look at the photographs on the first slide, talking about the sedimentation. At the edge of the sedimentation tank, we have to install a weir. So we install the V-shaped weir around the edge of the tank. So the weir length in this case is equal to pi d, or 2 pi r. So this is a kind of weir length. So we have to install a sufficient weir length for the sedimentation tank in both circular tanks and the rectangular tanks. So these tanks require sufficient weir length to maintain the water stagnations in the sedimentation tanks. So if we don't have a sufficient weir length, some turbulence may tend to occur inside these tanks. The reason why we install the weir is we want to minimize the turbulence. We want to minimize the effects due to the induced currents at the outlet. That is why we have to install this equipment. Actually, this weir, I think, I assume it's if you take the hydraulic engineering laboratory, you will be having a chance to monitor how the water flow through the weir. They will provide you both rectangular weirs and the V-shaped weir, but you only observe the flow through the weirs. But on the other hand, in the sedimentation tanks, we used a weir to actually minimize the turbulence inside the tank. So we installed this weir around the edge of the tanks, or at least at the outlet. Okay, so for a weir loading rate, it is equivalent to the Q divided by the weir length. The thing is, normally weir loading rates will be given. We apply this value to determine the proper weir length. because the flow rates it's a kind of the questions you have to uh, it's a kind of the problems you have to find out this VL-link. So anyway, this value will give a proposed VL-links in terms of the size, and for the in terms of the operations, we used these parameters to investigate whether the VR we install are sufficient for the VR loading rates or not. The last one is the solid loading rate. Solid loading rate, sometimes it defined as the kilograms suspended solids per square meters per hours. So according to this unit, you can figure out. So it is equal to the kilograms per hour. Kilograms per hour is actually the solid load. Solid loads is suspended solids concentrations multiplied by the flow rates. So it will give kilograms per hour or kilogram per day. And if you divide it by the surface area, so the unit comes as the per square meters, or you can divide it by the volumes. So if you divide it by the volumes of the tanks, so it will be kilogram suspended solids per cubic meters per hours or per day. So it depends on how they divided these parameters. This parameter is not the important design designing factors but important for the designing of the thickener in the sludge treatment, which we will talk about it again in the next two chapters. For the designs, we prefer to allow the overflow rates slightly smaller than VS. This is more or less like a safety factor. So we prefer the overflow rate slightly smaller than the settling velocities. So normally it should be around 80% of the desired settling velocities of the particles to be removed. The settling velocities you can estimate by using these formulas, but these formulas in fact it's not appropriate for the flocculation settlings. It's only can be applicable for the discrete particle settling. These are the design criteria. As I told you, the value will be given surface loading rate for especially this table shows the values for the design, the values of the design criteria for the horizontal flow sedimentation tanks. These values are particularly used for the designing of the horizontal flow sedimentation tanks only, not for the circular tanks. For the circular tanks, we need another set of the design parameters, not this one. But this one is just an example of the horizontal flow sedimentation tank. The surface loading rate should be in a range of 20 to 60 cubic meters per square meters per day. A water depth, detention time, solids loading rate, this real loading rate. You can apply this value for the design of the horizontal flow or sedimentation tanks. So what does it really mean by the horizontal flow sedimentation tanks? If you still remember the figures I show you, the horizontal flow sedimentation tank. This is the one. Okay. So this is the one. These two are the horizontal flow sedimentation tank. Basically, the water. So just have a look at these figures, figure 86. So water just get into the chambers where this inlet, and then the settling zones applying around here. Uh, this is the settling zones of this horizontal flow sedimentation tanks. Water just flowing like this. This is the inlet, and then this is the outlet. So water just overflowing once all the suspended solids have been removed. So this is the settling zones. Okay. So it just go like this. And according to these figures, if you really have a look in the details, you'll find this one is the inlet. So number one is the inlet. Okay, water just get in here, and then going out, leaving this chamber where the outlet at the number 3. And what is the number 2? Number 2 is actually a kind of chains, flying chain system. So this model will drive this chain moving like this. This chain are actually equipped with the, you see this one? This is a kind of scratch. So if there is the particle, if there are the particles accumulated at the bottoms of the chamber, this equipment will try to force or push these settled particles to these directions, and before being kept in here. This is a kind of a hopper we use to collect the sludge after being precipitated. So these equipments are actually used to collect. It's a kind of the collector's arms to collect the settled particles and bring the particles to the collection chambers here. So it moves in these directions. It normally moves in these directions. I often ask the questions. So it's about the photo hunts. So you have to identify the possible errors shown on these photographs. So if I put the arrows in this direction, so you have to correct it because it's incorrect, right? Because this chain is supposed to rotate it in this direction. So according to these figures, so it has to move in a clockwise directions. But if it moved in the opposite direction, so all the suspended, all the settled particles will not be collected in this hopper. So you have to mention this arrow. It's actually incorrect. So this used to be a kind of final exam questions in the past years. So once it once it moved up, so somebody may question why this chain has to move up and reach the surface. By the nature, some of the suspended solids, especially in a case of the wastewater treatment plant, the sludge is organic substance by nature. Very often they have a kind of densities slightly or comparable, slightly lower or comparable with the densities of the water. That is why instead of it try to move down due to the gravitational force it moved up and floated at the surface, becoming what we normally call as scum. Okay, so it's just floating on the surface. So this changed not only pushing this setter sludge to the bottoms, but it also acts as an equipment trying to collect these scums and bring this scummed and uh, and leave it in a basket or in a scum extraction. So this is the equipment we usually call the scum extraction. So basically, it's a kind of the trash. We put it here just to collect the floating scums in case if it goes up instead of going down by the gravity. So this is a kind of the how the rectangular settling tanks work. On the other hand, other types of the equipments may be used like this one. They used like a scraper. This is the moving scraper, so it can move in these directions, and it also can move back again. So this we try to bring all the settled particles, uh, uh, then bring them into the hopper zones so that these particles can be collected here. After being collected, so if the concentrations or if the amounts of the sludge is higher, so there's a suction pumps bringing this sludge to the sludge treatment facilities again. So this is how we operate the rectangular settling tanks. It's slightly different from the circular sedimentation tanks, but this one is only used for the water treatment plant. It's only used in the water treatment plants. I rarely find the use of the rectangular settling tanks in the wastewater treatment plant. Okay. Uh, Maybe it's not suitable for the light particle setter because most of the wastewater treatment plant, the sludge coming from this plant is the organic sludge. That is why the circular tanks provide a better efficiency in terms of the removal and much easier in terms of the operation. That's why the in wastewater treatment plant they prefer to use the circular tanks and not the rectangular one like this. The tank, the plants that have the rectangular chambers like this, exactly same like this. So I have seen once I visited the provincial provincial waterworks authority somewhere in Chiang Mai province. They have been using this kind of system for the suspended solids removal after being coagulated and floculated. So this is how we how they used the rectangular chambers to remove the suspended particles. So that is a kind of figures. Then we just come to the example. So how we can make use of this criteria. So hopefully you are with me on this screen. Okay. So this is the question. Sedimentation tank is being designed so that it will remove 100% of all particles which have the settling velocities of 0.3 millimeters per second. So this is the information. 100% of the particles which have settling velocities of 0.3 millimeters per second. So what does it mean? it means that this information try to tell you that this sedimentation tank is designed to remove the particles which has the settling velocities of the 0.3 millimeters per second. For those with the smaller settling velocities will not be 100% removal. The percentage of the removal for the particles with this settling velocity are smaller than 0.3 millimeters per second. So it's equal to the settling velocities itself divided by a 0.3, and then you can find out the percentage of the solids removal. So these informations will give you some idea about the what size of the parameters will be used as to decide the factors for this particular sedimentation tank. So basically, this is the VS, but this VS is theoretically speaking, for the optimum design, this VS must be equal to the overflow rates. The design criteria is the overflow rates, not the settling velocities. But according to the optimum design, the settling velocity should be equal to the overflow velocity. So we will take this information as the overflow rates or overflow velocities VO, which is also equal to 0.3 millimeters per second. There are two questions for flows of 10 cubic meters per minute. You have to find out the dimension for the rectangular basins. The rectangular basins is something like this. So the figures I just show you, this is the 3D sketch. This, according to these questions, you have to, once you get the values, you should allocate this value onto this sketch. Without the sketch, there will not be any meaning to describe your design. So the answer should be always with the sketching like this. It's important with some kind of drawing. So all the engineering works has to be illustrated in terms of the drawing. Okay, for floats of 10 cubic meters per minute, you have to find out the dimensions for the rectangular basins in which the length is 4 times to the width. So the flow rate is 10 cubic meters per minute, while the length with respect to the width is 4 is to 1. So this is the ratio. And the detention times we pick up from the criterion table. It is 2 hours. So we already have the flow rate. We already have the detention time. We will now calculate the volumes. We will be able to obtain the volumes. From this criteria, it gives the overflow velocities. So according to this criteria, we will be able to find out the surface area, as the surface area is equal to Q divided by VO. In fact, overflow rates is equal to Q divided by AS. So just rearrange these equations and then substitute all the values into this equation. Then you can find the surface area. The surface area is equal to the length into the width. But the length is 4 times of the width. Accordingly, you can find out the width into the length with respect to this information or these values. Okay, so now you can obtain the length and width from the overflow velocities or the overflow rates. And then what is next for the right now you don't know the appropriate depth, but appropriate depth can be simply determined because here the detention times is 2 hours. HRT is equal to volumes divided by the flow rates, so that the volumes is equal to Q into the HRT. you can automatically determine the volumes based on this information. The volumes is equal to R length into the width into the depth. But from the previous criteria, you have already get the length and width. So at the end, you can find out the depth. You can simply determine the depth by considering the length and width obtained from the previous calculations. So now the volumes of the tanks we have already determined with length and the depth or the height. So these are the answers to the first question. Then the second question determine the total wheel length required if the wheel overflow rate is 250. Show how you would locate this wheel and the sketch on the basis. So basically, you have to find out the wheel length. Wheel loading rate is equal to the flow rate divided by wheel length. The flow rate can be simply obtained from the previous question. The values is already given, and the criteria is 250, so that you can find out the wheel length, which is equal to the flow rates divided by 200 cubic meters per cubic meters cubic meters. This one is the cubic meters per day. This one is the meters. So at the end, the wheel length is expressed in terms of meters or in terms of the length only. So finally, you can find out the proper wheel length. So for the rectangular chamber, how we normally install the wheel. So you may look at this photo. This is a kind of horizontal sedimentation tank, just the same as I have shown you in the previous photo. For the circular tanks, there are a number of V-notch weir installed along the edge of the tanks. But for the horizontal sedimentation tanks, at the ends of the tanks or at the outlet zones, they may install several weirs like this. They can also do that. Okay, so where is just water is just overflowing into the outlet channel. So this is the outlet. Okay, this is the outlet. Weirs are installed in both sides, so water just overflowing like this. So the weir length could be equal to this one, and then also plus this one, L1 plus L2. And if you have many, you have to combine the total weir length. So how much would be for the total weir length, and just check whether it's a match or corresponding with the criteria or not. Okay, this is how we install the horizontal sedimentation tank, because if we only install at the end of the tanks like this, the length may not be sufficient. Okay, length may not be sufficient. So if you just only install at the edge of the tank, at the end of the tanks, especially for the rectangular chamber, mostly we need extra outlet for the this case for this rectangular chamber. So at the end, you have to show us. So how would you install this weir? So whether it will be something like this one, or if you have another idea for the installations of this weir, but anyway, it should be located at the end of the treatment zones. Okay. So these are all about the sedimentation tank. So I'd like you to show you some photographs in material. Here it's also the rectangular chamber, but very special because at the inlet, if you really have a look here in a figure B, there are many holes on this wall. So water has to pass through this hole for entering to the settling zones. Water has to pass to these holes. What are the beneficial use of this hole? Why we need to have this host? The host installed at this position before water entering to the set link zones like this. Do you know what is the major purposes of installations several hosts like this? So we want this hole to becomes a part of the coagulation process. So the coagulants may be added somewhere near the entrance, but once the water get into this chamber, so it has to pass this hole. So if you make a large hole, or you have like several holes on the wall, water just can actually pass the hole smoothly. So very small mixings will be created. But if the size of the hole is small and you have a less number of the holes on this wall, a lot of mixings will be created, just like a case of a pipe. So this is a pipe, water just flowing like this with the flow rates Q. This Q is equal to A into V, areas into the velocities. But once we install the orifice, the opening areas it's small, it's smaller. So this settling velocities becomes V2, and the areas becomes A2. So the settling velocities at this point is actually increased as the areas decreased. It is also the same as this one. So we need the proper areas. It shouldn't be too high. It should not be too low. The opening areas of the entire hole, because if the we make a hole like this, increase of the velocities will result in an increase of the TDH, or the total head. So if we can increase the total head, we can actually promote the power. The higher power will be resulting the higher gradient velocities. Okay, so the higher gradient velocities is actually not good for the flocculation process. That is why we need to maintain the proper areas of these holes, opening areas of these holes. Okay, so this is a kind of combination of flocculations and our sedimentation process. I think for the coagulation, they also add the chemical somewhere here. Okay, maybe a figures in this slide, it would be better. Many plants, water treatment plants in Bangkok, they use this kind of the combined coagulations, flocculations, and sedimentation process to purify the water. So this tank, on the other hand, it is called the accelerator. Accelerator. This is the one, accelerator. So the tanks is simply divided into two zones. Okay, just have a look in this figure, maybe more clear. So these tanks, uh, uh, it's in fact the circular tanks. Okay, it's in fact the circular tanks. So these tanks, this buffer would actually separate these tanks into two compartments. So this buffer, it's more or less like a skirt, ladies' skirt. You have to think in 3Ds. It's like a skirt, and here is also a buffer uh, separating the outer compartments and inner compartment. So how does this tanks works? Chemical and coagulants are added here in where this pie, and inside these tanks, at the centers of these tanks, they install a kind of motor equipped with the shaft and connected with the impeller, loaders impellers. There are only one impellers here. Okay, there is only one impellers here. Create the mixings, but the problem is if you consider the upper part. So this is the upper part, and this is the lower part. The upper part, the volumes is divided as the V1. So if we define these volumes as V1, and this volume it's given as the V2. So according to the figure, you can actually see that V1 is much smaller than V2, right? So if we compare the mixings which occur in the first compartment and in the second compartment by considering a G for the first compartment and the second compartment, G is equal to square root P divided by mu V, right? This one is also equal to P divided by square root divided by mu V. As uh, they are the same equipment, but they actually work in two zones, but they are the same equipment, so that the power is the same. Okay, the power remain unchanged in the first and second, so it's the same. But the only thing which makes the G in the first compartment and the upper compartments and lower compartments difference is just the volumes. Okay, uh, number one, volumes is small. This one is small, but number two, the volume is large. Okay, so you can expect it. What will be the values of a G in the compartment one, and what will be the values of a G in the compartment two? A G in the compartment one tend to be higher, but G in the compartments in the lower compartments tend to be lower because the volumes is larger, although they are using the same equipment. Okay, this is how it works. So we use the same equipment, but the volumes, working volumes are totally different if by using the buffer just to separate each compartments like this. And once the chemicals reach all the particles, and the particles are completely mixed, and flux in the lower compartments are formed. So several flux are formed here in the lowest compartment. And as the water always get into this chamber, at the center of the tanks. So some of the water which get inside must lift these inner compartments to the outer compartments. So this is normally considered as the outer compartment. So this is the outer compartment. So you have to keep it in mind. This is the circular tank. Okay, this is the circular tanks. You have to think in 3D. Okay, so out outside, this is the zones we use to remove the slush. So this is the zones we use to remove the slush. Outer layer, outer compartment. So this only happens in the outer compartments. Water which have been mixed and the flux are formed will move out to the outer compartment where this and some are coming out like this. So anyway, all the suspended particles will be accumulated here. The sedimentation process will be expected to occur in the outer compartment. But if you look at the bottoms of the sedimentation zones, the concentrations of the sludge. So this is the sludge in the sludge settling zones, or the concentrators would be very high. So this will actually act like a blanket. So for a small particles which are formed, colloidal particles forming the flux, so it becomes bigger and heavier. So they are trying to move out along with water. But once it reach the sludge blanket, or the suspended solids will be accumulated in the sludge itself. So it will not goes up with the calified water. Okay, so this is how it works, and as we maintain a high concentrations of the sludge here, that is why these types of the settling tanks we normally call the sludge blanket califier. Okay, this is a kind of the sludge blanket califier because here we maintain the concentrations of the sludge to be very high. Highly concentrated. So this act like a blanket. Whatever the small particles getting out where this blanket, it will be captured. So they actually act like a filter. Okay, for the small particles will be captured inside these blankets. Only very fine particles will be moving up. But anyway, once it reach the other particles, so it again settles to the bottoms. So only the supernatants or cleared water, sometimes we call clarified water, overflowing to the effluents. So this is how the sludge blanket califier work. Another examples of the sludge blanket califier is this one, figure number 96. For the figure number 96, this is also the sludge blanket califier. So by the name, you should be thinking about the blanket or the filter layers. They actually act like a filter layers. So we maintain a high concentrations of the sludge at the bottom zones of the tanks. So once all the small particles get into these zones, that five particles will be captured by the old sludge, which we maintain it inside the tank. So for the this tank, this can be a rectangular tank or it can be a circular tank. So it can be both. These types of the tanks, the Metropolitan Waterworks Authority, they also used at the Mahasawat water treatment plant. So if you really have a look in the video clip that I leave it in the Microsoft team, I think you will find photographs of this chamber, but you may not know what it is and how it works. Okay, for this tank, so how it works, this is also the combined floculator and the sedimentation tanks. Three processes are occurring in this chamber. One is the coagulation, so chemicals are added here, and then liquid just get into these tanks via this pipe. So this is the entrance. So the entrance, the water will enter to the tower, central tower in this tank. So this look actually like a tower, but in fact it is just the chamber which we can actually regulate the pressure. This is the valve. We can actually regulate the pressure. So when the water get into this chamber, central chambers, if we suck the air out, so this chamber becomes a vacuum. Okay, it's become a vacuum. So it gives a negative pressure. So once it gives a negative pressures, once the negative pressures is applied inside this tower, what will happen? Just like if we suck a water, water levels will increase, right? Water levels will increase. But if we let it goes up, water levels increase for some times, and immediately we open this valve or release this valve. So once we open this valve, the pressure inside this chamber will be equal to the atmospheric pressure. So once the pressures inside and outside are the same, and with the gravitational force, all this water will move down. Okay, so this is how it works. And then once it moved down, it moved to this number 9. This number 9, it's the perforated distribution pipe. So water just flowing through this pipe and then moving like this, overflowing to this channel. Okay, so here it's also the sludge blanket. So we maintain a high concentrations of the sludge. So high concentrations of the sludge actually act as the filter media. All the fine particles will be captured, the same as I explained it in the case of the accelerator. Okay, so then water just move up and then being collected where the effluent louder. Sometimes they use like they may apply a large PVC pipe and then they make a hole around. Okay, then they put it here in the surface. So it doesn't have to be always a VR installations, but it could be any, but that equipment we equip it at the outlet must be able to prevent unnecessary turbulence occurring inside this tank. Okay, so this is how the power settled clarifier work. You can actually have a look at in the video clips again, and then I'm sure that you will be able to find the photographs of these tanks at Mahasawat water treatment plant. So this kind of sedimentation chamber, we can actually maintain the overflow velocities as high as 3 to 5 meters per hour, or a cubic meters per square meters per hour. This is actually very high if you compare it with the settling criteria for the horizontal tank. So this one is only 20 to 60, but the unit is with respect to the day. But here, if you really take a look at the overflow rate, so it would be expressed in terms of meters per hour. 3 to 5 meters per hour is very high. On the other hand, another types of the pulsator, it's shown in a figure 97. So it's basically the same, but they install the inclined plate. They install the inclined plate. The inclined plate here is the same as this one. So this is the inlet. Water just need to go like this and overflowing during moving up. So this water has to move through the space in between the plate before reaching the outlet pipe or the water collection pipes up there. So water has to move it like this through the inclined plate. So this figure is also the pulsator, but uh, they are like an upgrade of this chamber, conventional pulsator chamber. This one, the pulsator califier, actually can process the water up to 3 to 5 meters per hour. But if we install the inclined plate, this chamber, the same chamber, can actually process the water up to 10 meters per hour. So what does it mean? The higher the settling tank, which can handle higher overflow rates, will be better. Why is it like that? The water handling overflow rates would be better. Because if you think about the definitions of the overflow rates is equal to Q divided by surface area. So if this tank can actually process the higher uh, uh, overflow velocities, it means that this tank can handle the higher flow rate. Okay, we can actually increase the production capacities if we used the tank which can maintain the higher uh, surface overflow rate. Or if you keep the same flow rates, but we change the operational mode. For example, installing the inclined plate. This one, we could make the surface overflow rates up to 10 uh, meters per hour. But this one, we can uh, process only up to 5 meters per hour. For the same flow rates, if we use this one, if we upgrade this one, uh, suppose this is a 5 meters per hour, and this is the 10 meters per hour. If you use this one, what will happen for the same flow rate? So if the flow rates, if the given flow rate is a Q, so if you go for this one, and if you go for this one, what will be the difference? The difference is the size for this one will be much smaller, at least smaller than this one by a half. Okay, so if you have, if you already have the flow rates, and if you use this tank, the uh, size will not have to be very high. So this is the beneficial use of the inclined plate. And now how the inclined plate can actually improve the qualities of the treatment. This is the answer. Okay, so this is the one. Why we need to use the plate and tube settler, especially inclined plate and tubed settler. So inclined plates, inclined sedimentation tank is something like this. This is the photographs of the inclined plate settler. So inlet is here. Water just move up and then overflowing to the collection pipe. So water has to move in between the plate, move through the space in between the plate. How this inclined plate or tube could actually increase the overflow velocities. So if you think about the space in between the plate, horizontal plates or the horizontal tube, so it becomes like this. The distance or the gaps is given as a d. So the space in between the plates or tube is given as a d. And if we make it inclined with the angle theta, so this still becomes, this is still a d, but a vertical distance between these two plates becomes d dash like this. And we can promote the mathematical expressions, relationships. A cos theta is equal to d divided by this d. Okay, so if theta is a 0, so it comes to these conditions. But if it's not equal to 0, for example, if the theta is a 60, the ratio between the space and the vertical distance is equal to 0.5. Okay, cos 60 is a 0.5. That is why this one is only half of this one, d dash, or this one is equal to twice of the space in between these two plate or two tubed wall. Alternatively, we can rearrange this equation so that we can determine the vertical distance. The vertical distance is divided as d divided by cos theta. Considering the settling zones for the horizontal settling zones like this. So these figures I have mentioned so many times, particles dropped into the water with the settling velocities Vs, and the horizontal velocities is given as V1. We can actually determine the maximum or V1. Okay, maximum V1, what is this? According to this figure, this is L, and the space in between the plate is given as D. So based on the similarities of the triangle, so you can take V1 divided by L, and it will be equal to the settling velocities divided by D. But in general, we make it like this. This one. So it depends on the theta. So if the theta is a 0, so this become a d. Okay, that is why maximum horizontal velocities is equal to VSL divided by d. Okay, so this is the how we obtained this equation. And the problem is if we make it inclined with the angle theta, just substitute this one by this one. So you will get this one. A horizontal flow, a maximum horizontal flow is equal to VL cos theta divided by D. Okay, but the problem is a cos theta is always less than 1. It's the point something, 0.5, 0.4, 0.6 something. It depends on the angle. So if this is not 0, if the theta is not 0, so the values of the V1 tends to be smaller. Okay, so if it tends to be smaller, what does it mean? So how it would enhance the suspended solids removal. So just think about the normal precipitation. So this is the VH and this is a VS. So normally you can find out the trajectory line. So the trajectory line would be something like this. Okay, it's a resultant of the horizontal velocities and the settling velocities. But in this case, if we make it incline, what will happen? The horizontal velocities will be smaller. So VS settling velocities remain the same. But if we could actually shorten the settling velocity, something like this, okay, the trajectory lines of these particles will change, becomes something like this. Instead of it reach the end of the settling zones, so it reach somewhere closer to the inlet. Okay, so this is how the inclined plane enhanced the removal efficiency. And if you want to upgrade the conventional sedimentation tank, you can simply install the inclined plate or inclined tube. Okay, so this is a kind of sedimentation tank. And okay, so this is the figures, the figures of the combined coagulation, flocculation, and sedimentation process. This units is actually called the accelerator. Okay, and if we want to increase the efficiency, just install the inclined plate like this. So this one would actually increase the overflow velocities or the capacities of the tanks to handle larger flow rate. Okay, so these are about the settling tanks, so that you can determine the size, and if you want to upgrade the tanks, you can install the inclined plate. So how the inclined plate would help to increase the removal efficiency. Just like we reduced the flow rates so that we can obtain it the shorter the trajectory lines, so it doesn't have to reach at the end of the settling zones. Okay, it settles faster. So if we could actually reduce the horizontal velocity. Okay. Okay, so that is all about the sedimentation tank. There are something which we need to keep in mind during the operations of the sedimentation tank. As I told you many times, water in the sedimentation tanks need to be kept stable. So there should not be any turbulence occur inside. So the turbulence comes from the currents, normally comes from the currents. There are several types of the currents which occurs inside the sedimentation tanks. The one which you may be familiar is a kind of inlets and outlets induced current. So water is overflowing. So once it overflows, some kind of movement in this chamber usually occur, and it tends to move up. So this is a kind of currents induced by the inlet and the outlet. So we should actually avoid settling zones. Effective settling zones should not be disturbed by the currents that may occur. Other types of the currents, if for example, it is due to the densities difference. The hot water normally it's lighter than the cold water. Uh, During the winter, near the surface, the temperature is low, and then down 1 meters or 50 centimeters below the surface, the temperatures can be higher, so it becomes lighter, so that the light water we tend to move up, and the heavier water tends to move down, so that mixings can actually occur. And sometimes we have to be aware of the surface currents induced by a wind, especially for the large sedimentation tank. The tank that for example, the Bangkok Metropolitan Authority used, Waterworks Authority used, the diameter is 65 meters, which is quite a large. It's even larger than the swimming pools. So there's a very high chance that the surface currents will occur due to the wind. So this will disturb the sedimentations of the particles. So we have to be aware of this. Eddy currents is actually the currents occurs due to the inertia of the incoming liquids. I assume that the eddy currents you have already started or learned it in, I'm not sure, in fluids mechanics or in the hydraulic engineering. It's a kind of currents usually occurred by the inertia of the liquids. If you stand on the bridge, and if you really have a look at the columns, water flowing to the columns, and if you observe on the sides behind, uh, you will find some currents occur. So this is a kind of the currents occurs due to the inertia. We normally call it an eddy current. So this is the current normally occur in the sedimentation tanks. And what we have to be aware during the operations is the short circuiting. This is not only for the sedimentation tanks, but for all the tanks used in water and wastewater treatment plant. I have already mentioned about these problems when we talk about the mixing chamber. So we need to prevent the short circuiting. The short circuit, what does it mean? It means that water is supposed to be staying inside this tank with the times equal to V divided by Q. But instead of they spend the times inside this chamber equal to V divided by Q, but it takes a shorter times. So we can actually say that water elements has got a short circuit. So this we have to be aware. We can actually prevent this phenomenon by using a proper inlet and outlet design. Another problem with the sedimentation tanks is the scald of the bottom deposits, especially in case of the wastewater. Wastewater, the sludge is mainly the organic-based sludge. So if we keep it the organic substance for longer time, there will be some degradations. So if the degradations occur in this sedimentation tank, so it may generate some smell, or it may create some bubbles. You may have heard about the anaerobic process or the anoxic process. is a condition where there is no oxygen in the in the bottoms of the tanks. So this is actually the biological process used to degrade the organic substance. So under anaerobic conditions, the organic could be degraded and methane gas is formed. So you find the bubbles of the methane gas coming up, or the nitrogens occur due to the denitrification process. So this is also possible that may occur uh, in side the sedimentation basins. So this is all about the settling tank. And now we will move to the next unit operation, which is also very interesting. The filter. Filters is also one of the most important uh, unit operation uses in the water treatment plant, but we rarely use this one in the wastewater treatment plant. The objective is to remove the inorganic and organic particles from the water and wastewater, but we rarely used in a wastewater treatment plant. There are two types of the filters. Uh, Pressure dewatering filters. It is nothing but we just apply the filters. But the one which is widely used in the water treatment plant is the gravity filter. A gravity filter is nothing but just let the water flow to the surface of the media, and water will seepage through the porosities of the media. There are two types of the gravity filter used at the water treatment plant. We classify it based on the filtration rate. So if it goes fast, we call it a rapid sand filter. If it goes very slow, we call it a slow sand filter. So we have two types of the filters, SSF, slow sand filters, and the rapid sand filters. Physical characteristic of these two types of the filters are more or less the same, but it's just only a matter of the size of the media. So if you are using a sand as the media, uh, if you take the bigger size of the sand, so it can actually give you a fast filtration rate. And in that case, we normally call it a rapid sand filters. But if you used a very fine uh, particle as the media, and that filters could be considered as the slow sand filters, because the smaller particles in terms of the porosities will also be smaller. Small space will result in a slow filtration rate. So this is a kind of a gravity filter. So it can be actually opened to the atmosphere. Water just enter to the chamber at the top or at the surface of this chamber, and then it just move through this media. So in general, we use the sands as the uh, filter media, but in some cases, they may also use the cover. In some cases, they may also use the charcoal. Uh, in fact, using charcoal could post some benefits, as if the water contains some taste and odor, charcoal can actually absorb that the compounds associated with taste and odor generations. So that here you can see there are three different types of the media used in these filters, but the most commonly used is the sand. Okay, gravels and charcoals, it depends on the types of the water, or it depends on the designs, but mostly the sands is the a kind of the major filter media used in general. For the removal mechanisms, how the filters can actually remove the particles. For the first school of thought, we may think like the big particles will be retained in the media itself, but in fact, not only just the big particles retain it. Some other mechanisms also occur in the filtration chamber. For example, adsorption. Here is the figure describing an adsorption process. Small particles can actually get adsorbed. Adsorbed, if you really pay attention here, this is not misspelling. AD adsorption, not AB. Okay, so if I use the AD, it means that it goes and stick onto the surface only, so it does not penetrate it inside. But if I use like a AB, for example, the bacterial cells, they absorb the food from outside. That one is AB. B is used to describe that phenomenon. All the food get inside, penetrate to the cell's walls. That one is adsorbs, but that one is absorb, AB. But here we are talking about the adsorption. Adsorb, it's only it refers to the particles just get onto the surface. Stick onto the surface like this, does not get inside the media. This is the photograph. This is the pictures describing how the adsorptions occur. So there are several processes that can occur inside the filter media, not just the big particles retained in the media. For the particles, those with the size smaller than 0.5 D. D is the average diameter of the media. For the particle size less than or smaller than 0.5 D, these particles will pass through the pore, but those bigger than 0.15 will be retained in the filter media, or sometimes it can be adsorbed. For this low sense filter, I think I have another versions of the slides. I'm not sure. So it will show the removal mechanisms, but this is not the version that I have. Okay. So if I have time, I could find another version. So I'm not sure about the in a Microsoft team which one I live there. I live it the version. Which version I live in? Class material lecture notes.นะครับแป๊บหนึ่ง sampling zones, and then we move to the removal mechanism. Okay, this one. So these are kind of explanations about the all the phenomena that take place in the filter media. Here is the figure summarized about the mechanisms within the granular medium. This is the filter media. It could be a sand or it could be a gravel. The particles coming inside the media layer, it may move along with a streamline and get attached. So this is a kind of interceptions, a movement, and finally these particles get absorbed. And for the sedimentation, especially for those with the heavier or the larger density, it could actually move not along with the streamlines of the water. For light particles and fine, very fine particles. So it moves without any uh, 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 moved not depending on the streamline. So this is a kind of a Brownian diffusion movement. So this usually occur with the small sized small particles. Some of them, especially very fine particles, just like the particles, clay particles or colloidal particles, it has a, high concentrations of the charge around the surface uh, due to its electrical interaction, so it may get attached on the filter media. So these are the possible mechanisms, transportation mechanisms, and also removal mechanisms that could actually occur inside this filtration layer in the filtration tanks. Uh, Okay, so we just come back to this slide, slow sand filter. In fact, the slow sand filters and the rapid sand filters, the key difference is just the effective size, all the media sized. So if you used the smaller sized, uh, your filters becomes slow sand filters. If you use the bigger media size, your filters becomes rapid sand filters. But for the slow sand filters, as the filtration rate gets slower, some other effects or phenomena will occur. Removal mechanisms will be something different from the rapid sand filters. For the slow sand filters, waters just gradually pass through the media. So this will enhance the establishment of the biologically active layer near the surface. This one, they actually name it specifically as the smoothest layer. So this will occur at the surface of the media. So this will grow up and this will actually be beneficial for the suspended solids removal because they can actually retain it in these contaminants in these layers, both the suspended solids and some of the pathogens or the microorganisms. Uh, for this one, we don't have to clean it on the daily basis. We can actually clean the filter once in 3 months or once in a month. It depends on the turbidities or the suspended solids entering to this chamber. Remember that the suspended solids of the turbidities could be very low because these filters, in general, they received the treated water from the sedimentation chamber. So normally the turbidity is very low, but sometimes it could be higher than 5 NTU. But in general, it's already past the drinking water quality standards. But we still need to have a filters because sometimes during a wet seasons, the incoming turbidity is higher. Uh, the performance of the sedimentation tanks may not be consistent. So in that case, uh, this may be a major reasons why we need to have a filter. We just want to produce reliable water quality with no extra the turbidities found in the effluent. The bed is cleaned manually and the surface, the tops approximately 5 to 8 centimeters of sands is removed because this layer will be full of the biological active layers. That is why somehow we have to remove it. We cannot let it gets blocked. So if we allow the growing of the biological layers, if we allow this grow up, so it may block the uh, pores. Water can pass through it efficiently. The fire sand load at the lower rate, the filtration rate. Actually, this is the filtration rates. It usually are in the range of 0.05 to zero point 0.2 meters per second. What does it really means by the filtration rate? Filtration rates, you have to think about the how water moved to the filter. So it moved like this. Actually, it moved like this. This is the flow rate, Q, before being collected at the under drain perforated pipe. So the important thing is the surface area again. So if we take the flow rates divided by filtration surface area, this will be divided as the filtration rate. And of course, the units of this filtration rate is meters per hour, or it can be expressed as the cubic meters per square meters per hour. So it is more or less like a overflow velocities, but in the case of the settling, in the case of the filtration chamber, we would never talk about the overflow velocities because it gives different meaning. So here we are paying attention on the filtration rate. It's also equal to the Q divided by the surface area, but this is not the overflow rate. So it's give a different sense of the explanation. Okay, so raw water turbidity must be less than 50 NTU. So we can apply the raw water directly to the sand filter if necessary, but anyway, it must not exceed 50 NTU. Usually we can allow up to 10 NTU. The removed sands, we have to remove the top 50 to 80 millimeters of the sands from the surface. Then this sands, we have to be cleaned, and then once it cleaned, we can reuse it again. So we don't have to waste all the sands fully covered with the biological layer. So we can just remove, clean, and then reused. Even we have to do it once in 3 months. Okay, so these are the typical characteristic of water resources in terms of the NTU, or the turbidity unit. NTU actually stands for the nephelometric turbidity unit. So I hope you're already familiar with this term. The lake, generally, the turbidity is around 1 to 20 NTU. The river, it's normally in ranking from 10 to 4,000 NTU during the dry season. The turbidity may be very low, but during the wet seasons, where there is a slide or landslide, the turbidity could increase up to 4,000 NTU. But anyway, the required for finished water should be approximately 0.3 NTU. This is the case of the slow sand filter. Mostly the system strive for less than 0.1 NTU. Okay, or a non-detectable limit. Even though the filtration rate is very low, still there is some advantages to use this slow sand filter. as the slow sand filter could actually produce the water with low levels of silica, iron, and aluminum concentrations from the industry used. All these metals can be absorbed onto the filter media surface as it moves slowly, so it enhanced the immobilizations of these metals. No pretreatment is required, no chemical required. But for rapid sense filter, coagulations and vacuolations are a must to have a process. For the slow sand filter, if we used good quality raw water, for example, groundwater, uh, we don't need any coagulations and vacuolation process, but the only thing is we need to maintain if the surface water contains something less than 50 NTU. So it is possible to use this without any pretreatment, without any coagulations and vacuolation process. Good bacterial removal capacity. As I told you, this is due to the lower filtration rate. Effluence is less corrosive. Filter runs is relatively long. Uh, uh, Corrosions in water, acidities in water normally comes from the dissolve of the carbon dioxide. So if we use this um, kind of a filter, carbon dioxide is partly stripped out, so the water becomes less corrosive. Disadvantages, the flow rate is very low. So if you want to produce the large quantities of effluents, you need a large area. But this one is not good in terms of the color removal efficiency. And if the turbidity is greater than 50 NTU, it may not be very efficient. And sometimes it causes nuisance conditions due to the microbiological and microorganisms growth. Now we move to the filters. This is the types that is widely used, as it can actually process up to 5 to 15 meters per hour. 5 to 15 meters per hour. This is the filtration rate. So if you compare it with the slow sand filter, it can actually process up to 0.05 to 0.2 meters per hour. So it is a lot more faster, a lot faster than the slow sand filter, approximately 100 times faster than the slow sand filters in terms of the filtration rate. Biological activity played no role because the filtration rate is very high. How does it look like? This is figures describing the components of the rapid sand filter. Here is the filter medias, and then we put the waters above the filter medias. So water just passed through the medias before being collected, where the pipe networks in the bottoms of the chamber. This is the main pipe, or typically we call a manifold, and lateral pipe. We also use this pipe to collect the water. But the things that we need to have for the rapid sand filter, it's this one. See at the near the tops of the chamber, there is a kind of a channel. This one we normally call a wash-through channel. This is an equipment we need to have for a rapid sand filters. For a slow sand filter, the wash-through channel is not required. So what is the beneficial use of the wash-through channel? The watch-through channel is actually used for the normal operation. Watch-through channel it's not necessary, so we don't use this one. But for the rapid sense filter, as the filtration rate is very high, so that it could actually get clocking very fast. So if the suspended solids is high, so the filter may get clocked within 5 or 6 hours, or anyway, it depends on the suspended solid concentrations, or it depends on the turbidities. So if it lowers this filter media in the rapid sand filter could actually last longer than 2 days, but at least once in 2 days or once in a day, we need to clean the filters. So how do we clean this filter? For normal operation, water just pass through the filter media by a gravity. That is why these types of the filters we call gravity flow gravity filters. But if we want to clean the filter media, if you want to watch the dirt which get clogged inside or in between the pores, so how do we clean it? So we need to put the cleaned water or the treated water in the opposite directions. Normally, this manifold is used to collect filtrate water. But if we want to clean the filter media, we need to put this clean water through the manifolds, and then it will release the treated waters or the clean water into the media layer. And finally, we let it go for at least half an hour, so that water just get uh, uh, in an opposite directions. So watch through channels actually act as the effluent channels. So it's a kind of the channels receiving the water after used to clean this filter media. So feeding the clean water through the manifold just for cleaning the filter media. This process we normally call a backwashing process. We call it backwash. Okay. So wash through is necessary during backwash. So water just move up, just like a case of the sedimentation tanks. So water just get into the tanks from the bottoms and then move up and then overflow through the washed through channel. So the water containing a lot of dirt will be collected to the wash through channel. So this is the process we normally call a backwashing process. Rapid sense filter, other aspect like we need coagulations and floculations before the rapid sense filters. Optimum filtration occurs when the suspended solids in depth filtration impurities will pass through neither pass through the bed nor did or stain on the surface. Absorption would occur. Our significant amount is retained. So I just read. This is also another photograph showing all the components of the filter. Below is the perforated pipe. This is the manifold, and this is the filter that sand. Okay, when we talk about the sand, so it's like it's just like a pie. So if we put something in the pie, so it reduced the cross sectional areas, and if the cross sectional areas reduced, the velocities will increase. Increase of the velocities resulting in increase of the head loss. Okay, the head loss will increase. For the filter media, These are the criteria for the selections of the filter media. So we select the media based on the grain shapes, rough material, smooth sands. If we want the smooth sands, we normally take the smooth sands from the river. The best one should be an Ottawa sand. So have you ever heard about that? Ottawa sands. But the Ottawa sands is very expensive in Thailand, and probably in many countries we don't use the Ottawa sands as the sands medias. We mostly use the river sands. Sea sand is not preferable. Mostly we use the smooth sands. I don't know why, but sea sands is not. Actually, we have a lot of sea sands in our Earth, but in terms of the filter medias, we sea sands is not good in terms of the absorption. River sands would be better, gives a better results in terms of the suspended solids removal and also the fine particles removal. Porosities or the packing densities could be around 40 to 60% lost by acid attacks. This we also need to pay attention because some of the medias it's a little bit sensitive to the acid attack. Because water it's sometimes contains some corrosive carbon dioxide gas, especially groundwater. Uh, uh, there are some certain amounts of the media we lost friability. For example, the anthracite would be more fragile. So if we used for a long time, we may lose some certain amounts of the anthracite due to its physical characteristic. But anthracite is good in terms of the odor and taste removal. When we talk about the filter media characteristic, the key factors, whether we will go for the rapid sand filters or the slow sand filters, depends on the an effective size. An effective size is P10. So if you still remember the experiments that you practiced, I think in the second year, you have done it, material testing. So you have to do the sieve analysis and then you have to plot the normal distribution, something like this, right? But for the filter media, we also make use this information to select the proper size to be used in the filter. For the sieve analysis, we normally take like 10 grams of 100 grams of the materials and dry for at least 4 hours in 120 degrees Celsius and then cool. Pass this amount, pass this material through the sieve mesh and then plot the curve, calculate the wedge percentage, and then establish the curve. Determine the effective size. So we only take the for the rapid sands filter, the effective size must be 0.8 millimeters. Effective size of the P10s of the sands must be 0.8 millimeters. But for the slow sand filters, the effective size of the sands to be used in the filter must be 0.5 millimeters. So the size is smaller. That is why it yields slow filtration rate, so that we call these filters as the slow sand filter. Another characteristic of the sand is the coefficients of the uniformity. Coefficients of uniformity refers to the P60 divided by P10. If it close to 1, it means that very uniform or very narrow distribution. Geometric mean size is P50. I think you all know about this. Geometric standard deviation size is equal to P 50 divided by a P 60. So if you do the sieve analysis, then you will get accumulative plot like this. Or if you plot the normal distribution, you will also get something like this. These are the typical properties of the filter media used in the rapid science filter. Sometimes we use the garnet, or sometimes we use laminate. Sands is the most commonly used. Anthracite. GAC is the granular activated carbon. Granular activated carbon. Okay. The effective size of the sands normally it's in between 0.4 to 0.8. Anthracite is a lot bigger. Anthracite is a core. It's basically a carbon. Granular activated carbon, it's also 100% carbon, but it's active. It's very active as compared to the anthracite. Very active in terms of the absorption because they burn, and then they are very, the surface area is very much larger than the anthracite. The filter media that we used in the household in a column, they said it's the filters, but actually if you open that filter columns or the filter cartridge, it is basically the granular activated carbon, not the sands and not any other material. So they are mostly the granular activated carbon. So if you remove the filter cartridge and take a look, uniformity coefficients for the sands, it could be in the range of 1.3 to 1.7. Density, it's 2.65 for the sand. Garnet is much heavier. Porosity is 40 to 43% for the sands, and garnet it's more porous. Hardness, sands is of course very hard. Hardness here doesn't mean the concentration summations of the polyvalent cation, but it really means the hardness. Okay, then units it's measured in terms of more. Anthracite, it's not very hard. Granular activated carbon, it's also not very hard. These are the summarized the typical properties of the filter media. Before moving to the initial problems of the rapid sand filter, I'd like to explain about how we classify the sands and then how we make use of the information after we do the sieve analysis. So how we can put the media with an effective size of 10 millimeters for the to be used in the filter media. So now I'm on the page of the PDF files. I hope you are all here. I feel like I have been talking alone for 2 hours already. Very quiet. No any response. No response from all the participants. ยังอยู่ใช่ไหมฮะ
อยู่ค่ะ
เดี๋ยวผม
อยู่ค่ะ
เดี๋ยวเราจะกลับมา
อยู่
เอา
ครับ
พูดถึงเรื่องยุ่งๆนะแป๊บหนึ่งเดี๋ยวขอเบรกแป๊บหนึ่งนะฮะjust maybe 5 minutes break, then we come back for this slides. Anyway, I think before the class, so I have left these files in the Microsoft Teams, so you can actually download it. So the files with the handwriting. แป๊บหนึ่งนะขอเบรกประมาณสัก5 นาทีขอไปยืดเส้นยืดสายก่อน เดี๋ยวนับแป๊บหนึ่งนะครับโอเคสถานการณ์ล่าสุดนะฮะมียอดวันที่ 21 นะครับผู้ติดเชื้อมหาวิทยาลัยธรรมศาสตร์2 คนนะนักศึกษา 2 คนยอดสะสมวันที่ 7 ถึง 20 เมษายนนะมียอด 61 คนนะฮะถ้ารวมวันนี้อีก 2 ก็เป็น 63 คนนักศึกษา 55 คนเป็นคนไทยต่างชาติ 1 คนอาจารย์ 3 คนเจ้าหน้าที่ 2 คนไปติดจากไหนมากันเยอะแยะเนี่ยOkay, so we just continue from what we left before taking a break. This is the first. So I'm gonna share the screen. Okay. Proper size selections. You can download this file from the MS Team. These files it's actually supplementary documents. This is the details about the how we can bring how we can actually take the natural science and then we have to remove the two phi fractions and the two cost fractions from the natural science, and then we only used this science for the making for using it in the filter media. Normally, if we take the river sands and then we perform a sieve analysis, we will get normal distributions, something like this. Some of them will be too far and some of them will be too cost. We don't want the two files and then the two cost. We only want this part. This is normally called a usable. Okay, for the usable sands is normally only half of the raw sands. For example, if we want if we want the usable sands or the sands which we will use in the filter for 1 tons or 1,000 kilograms, so we really need 2,000 kilograms of the raw sands or the natural sands. And then we remove the two phi fractions and then we remove the two cost fractions. So only this part can be used. Normally, okay, this will be better so that you can see overall details. For the stock stands, usually from the stock sands, these fractions P60, the difference in between P60 and P10, this usually contributes around 50% or half of the specified sands of the total stocks are usable. So according to this and according to this the nature of the sands, we can say that the P usable is about twice of the P60, the difference between the P60 to the P10. This one is expressed in terms of the percentage, okay? Uh, less than P10 is to 5, greater than P60 is to cost. This one is the natural sands or the raw sands, okay? For the P usables is about it's the P60. This is the P60 minus P10, and the usable we need to take at least if we want 1,000 kilograms, we have to take it twice. So P usable is normally twice of the P60 minus the P10. And I put the star here and here. The star indicates the natures of the sands. Normally, the specified sands contains about 1/10 of the usable sands below the P10 size. So that the P25, P25 it's equal to P10 minus this one, 10% of the P usable. And as the P usables is equal to 2 into P60 minus P10. That is why the P25 it comes as the P10 minus this one. You just multiply 0.1 with 2, so it becomes a 0.2 P60 minus the P10. Okay, so we have already got the P25. And then if you want to determine the P2 cost, this is 2.5, and then this is 2 cost. The P2 cost is equal to the percent usable plus the P25. So P usable, this is the P usable is this one. 2 P60 minus the P10, and plus the P25 at this one. This is P10 minus 0.2 P60 minus the P10. So this become this will divide it as the P2 cost, which is equal to P10 minus 1.8. So you take this one plus this one. This is the equation 1, and then this is the equation 2. A combination of these two equations, then we get this one. P10 plus 1.8 P60 minus P10. Remember that when I'm talking about P, in this case, it refers to the percentage. Here, it's will be more understandable. So if I put everything in a figures, this is the natural sand. So after sieving analysis, if we plot the accumulate, if we plot the accumulations of the wedge, so we will get the curve like this. Somebody may call it an S curve. This is the natural sands. Our target is we want the lines let dry. This one is the sands we will use in the filter. The red one is the sands we will use in the filter. Now the question is, so how we can classify the natural sands to from the black lights to becomes red lights? Okay, the natural sands is something like this, black light. So if we plot it like this one, what is the P10? This is the P10, and then this is the P60. X-axis is the probability scale, and then the size distributions is shown in the x-axis, shown on the x-axis. So this will give you figures of the size So what is the diameters? If the P10, so what will be the diameters? For the P60, what will be the diameters, like that? So this one is the P10 for the natural sands. This one is the P10s for the natural P60 for the natural sands. But the two fines and two cost is defined like a the definitions that I just mentioned. P25, it's usually the specified sands usually contains the 10% of the usable sands below the P10 size. So this is the P10. The P25 usually contains 10% below the P10s. According to this statement, so we can define where is the P25. P25 is here. This is the P25. And what about P2 cost? P2 cost is the P usable plus the P25. This one is the P usable. And this one is the P25. Sorry, this one is the P25. And then this is the P usable. This one plus this one, the blue line will reach the P2 cost. So now you can see according to the green line, whatever smaller than P25 we removed, whatever larger than the P2 cost we removed. We only use this one. Okay, so after we take this one, then we will only get usable sands identified, or if we plot, you will get that straight line like this. So this is how we classify the natural sands to become a usable sands, or the sands which we will put in the filter. But the problem is, what is the key criteria for the sands, usable sands to be put it in the filter? We will select, we will decide the characteristic of the sands based on the effective size. So as I told you, for the rapid sands filters, the effective size for the P10 needs to be 0.8. But for the slow sand filters, it needs to be 0.5 millimeters. Okay, 0.8 and 0.5 millimeters. And what should be the coefficients of the uniformities? So if we pick like the coefficients of uniformities is the 1.5, so you can get the P60. So the criteria is the P10s and the coefficients of the uniformities, and then P60 is the one we have to obtain it from the criteria. For example, if we select, if we want the filter sands with an effective size of 0.6 and the coefficients of uniformity is 1.5, so you can find out P60. This is 0.6 and this is 0.9. So now you can find out the P10, and you can define it as the P10, and then you can define this one as the P60. Remember that this is the lines showing the size distributions for the usable sands, or this one. We want to remove some part of the natural sands identified by the classified by the black lines. We want the usable sands here shown by the red lines. Okay, so this is how we classify it. We have to cut some of the sands. We have to remove the smaller portions, and then we have to remove the larger portions. This is the theory behind it. Then if you really want to classify, this is probably the example. So I think I have already put it in the MS team again. This one. it is the same thing I just try to explain, but this one is an example. Uh, Actually, this is supposed to be your assignments, but anyway, it could be an example. So what will be the question? So I will just look for the question. Okay, so this is the question here. Available stock sands. Available stock sands has the following SIF analysis. These are the size and these are the cumulative wedge. So we will take this information. So this one is the here they mentioned about the stock sands. Actually, this is the natural sands. According to this, the information shown in this table, first you have to determine the geometric mean size. So of course, this is the P50 standard deviation, effective size P10, and the uniformities coefficients of the stock sand. So this is nothing. This is what you have done it previously in material construction material testing cost. And the second question is, if you want to take this sands and use it as the filter media, your criteria is you want an effective size of 0.6 and with the uniformities of 1.5. So what will be the standard size we have to use, and then at what size we have to remove? Okay. And the next question is, so if we want like 1,000 kilograms of the sand for the to be put it in the filters, so how much we have to prepare? So how many kilograms of the natural sands will be required? So this is the question C. And some extra questions D and E and F. So basically, this is the questions, and this is probably the solutions. Okay, according to the table, okay, so what you would really needs to do, you have to plot all these informations in the log graph, and this line is not a very not a straight line. The curve like this is the informations is the plots of the informations taken from the table. So this is the size and then the cumulative wedge. So we want this line. This is the desired sands, and this one is the natural sands. Okay. For the natural sands, it is nothing but just you have to put these informations into the glass. The size is 13. This is the one. You put the size here on the x-axis, and then this is the normal probability scales on the y-axis. So just put the dots here and then plot this accumulative curve. And finally, you can determine for the geometric mean size. So geometric mean size is the P60. So where is the 60? Remember that this is 1. This is the log scale. Like, so this must be a 1. This must be a 10. And then this must be 100. So we have to plot in a log scale paper like this. Then you have to find for the geometric standard deviation. So what is the P10? As this is the one, then you can find out for the P10. So this is the P10 of the stock sands. And then you can find out a P60. So where is the 60? This is 100, so this is the 60. So you can find out a P60. Okay. So for the first question, you can simply look for the answers from the graphs. But for the desired sands or the sands that we wanted, an effective size is 0.6 millimeters, and the coefficients uniformities coefficients is 1.5. So we know that according to the relationships coefficients uniformities coefficients is P60 divided by P10. So if we want P10 0.6 and uniformities coefficients is 1.5, so that P60 is the 0.9. P60 is 0.9. Now, how the desired sands will look like, where it's 0.6. So this is 10 to the power of minus 2 centimeters. Okay, centimeters. So 0.6 is here. 0.6. So where is the 0.6? 0.6 and 0.9. 0.6 and 0.9. So we establish this curve. You can establish this curve, not the curve, actually the straight line. So this one is the P10. Okay, this one is the P60. No, actually, it's P10s and P60 for the desired sands. But if you look at 0.6 and 0.9 from the natural sands, you will get actually P10 for the diameters of 0.6. It's 33.5%, and then for a 0.9, it's equivalent to the natural sands at P54%. 35.5 for these diameters, and 0.9 it's located at 0.54%. Why is the 54? So this one is the 50, as 54 it must be somewhere here. This is 9. Okay, so you can find out so that P usable it's equal to 2 into 50 minus 35.5. So it's only 48%. So P25 you can calculate it according to the documents I have just explained it. So P25 of the natural sands is 29.4%. So where is the 24.9%? 24.9%. So those with the size smaller than 0.56 millimeters needs to be removed. And what about the P2 cost? You can estimate the P2 cost according to the relationship that I have just explained, and it falls at 70 something percentage. So at 70 something percentage, then you have to look at this 70 something percentage, and then what will be the size? So what will be the size? So 70.4% falls at 1.4 millimeters. For those with the size larger than 1.4 millimeters needs to be removed. Smaller than 0.56 needs to be removed. This is too far. And if it is larger than 1.4 millimeters, this also needs to be removed. P usable, so that if we want 1,000, but only 41% is usable. So how many kilograms of the natural sands are required? if we require 1000, but P usable is only 41%, so that it is required like approximately 2440 kilograms. Okay, so this is the answer to the question A, B, and probably C. For D, E, F, I have already posted the solutions in the MS team. If you have times, you can look for these solutions. Okay. So this is how we bring the natural science, and then we cut off some too coarse and too far portions, and only the usable one that we put it in the filter, so that in the filters the science actually has the what the effective size and effective size of 0.6 millimeters, and then the uniformity coefficients of 1.5. Okay, we still have time. Okay, for the filter, another issue when we operate the filter is about the head loss. It is about the head loss. As I mentioned, when we put something uh, inside the waterway, channels, or it could be a pipe. So if we put something inside, it means that the cross-sectional areas get reduced, and if there is the water flowing passing through the smaller areas, the velocities will increase, and of course the head loss will also increase. So if you think like this is the tank, and if you think like this is a pie, if we put the cost stance, water is supposed to move smoothly to the bottoms, but there is a cost stance here. So it gets actually reduce the cross sectional area. So it will also create the head loss. But the head loss, if we do it like this, head loss can be simply observed as the water levels are shown in size these tanks. So if we keep on adding the water into this tank, water is supposed to pass through this media. Initially, it may pass smoothly. There will not be any water left inside. But if you keep on adding the water with the constant flow rates, if you keep adding the water with the constant flow rates, so if you keep not this pairs, okay. So if you add the water into these tanks with the constant flow rates, and okay, this could be an outlet. Okay, so this is the media. So if you keep adding the water with the constant flow rates Q, initially there will not be any water accumulated above the media. But once you add this water, what will happen is the clogging may occur. Then the pore or the cross-sectional areas gets reduced. The head loss will increase, and after operation it for some times, you will observe the water levels accumulated at the above the surface of the media. And if you still keep adding the water with the constant flow rate Q, water levels will increase. So if you don't do anything, if you don't clean the media, water levels will keep on increasing. And at the end, if we don't do anything with this media, water will overflow it. from the tanks. So because of the clocking, okay, this is an effect of the clocking. That is why this becomes an issue while operating the rapid sense filters. I'm talking about the rapid sense filters. So once it get clogged, we need to clean all the dirt. The process for the cleanings all this dirt we normally call a backwash. Backwash is applicable only for the rapid sense filters, not slow sense filters. Okay, only rapid sense filter, not the slow sense filters. Um, uh, this is the problems why we operate the rapid sense filter. Even we put up water, there must be always the initial head loss or the with the constant flow rates there will be the initial head loss. So you will be able to observe the water levels above the uh, uh, media. So even the filters is clean, there will be some certain loss there. So we have to uh, uh, consider about these problems. And if we don't clean it, if we don't backwash this media, water levels will increase. And if we don't do anything, water will overflowing. Okay. On the other hand, if we filter it for long times, if even though water levels will not overflowing, but you will still observe some of the turbidity increased. You will still observe the turbidity increase if you don't backwash for long times. Because just imagine all the pores get clogged and then full of the suspended solids and no more space. Then water push this water flows to this pore, so it may push some of the suspended solids coming along with the effluents. So at the end, the turbidities will increase. The problems while operating the filters, there are two issues. One is the head loss, and another one is the NTU, is the turbidities. So at the end, head loss will increase over the limits, beyond the limits. At the end, NTU may increase beyond the limits. So this is the problems why we operate the rapid sense filter. So there's an issues with the head loss and the turbidity. For the turbidities, after we operate for the initial times, the turbidities in the effluent. So I'm talking about the turbidity in the effluents. So turbidities, if you measure initially it will increase, but after operating for some times, a few minutes, or it may be several minutes and hours. It depends on the characteristic of the media. But anyway, at the end, so the turbidities will decrease. So if you make like a 1 NTU, so this will be smaller than a 1 NTU for a long time. Keep it constant. So after it gets clogged and filled with the particles, there is a chance that the particles may escape from the filter media. So in that case, if you measure in the effluents, the turbidities will increase. But how much time does it take to get beyond this allowable level? So these times we call the breakthrough times. These times we normally call a breakthrough times. In terms of the head loss, if we operate it for some times, there will be the initial head loss, and then if we keep on adding the waters into this filter, water levels will increase. We cannot let it increase beyond some certain limits, otherwise it will overflow. So if we plot the head loss with respect to the times, so it will be always something like this, gradually increased. But this is the limitation. So if it's increased beyond this time, so water will be overflowing. Okay, so this is the limitation. This is the times to reach the maximum head loss. This is the breakthrough times. Beyond these times, the turbidity is likely to increase. I mean, turbidity is in the effluent. Okay, in the designs and operations, engineers prefer to observe the head loss instead of the turbidities. Why? Because the head loss is simple. You can just look at and you can just measure the water levels. But turbidity is also okay. It's not difficult to measure, but at least there's some one or two more step extra. You need to take the sample. You have to get the samples and put it in the turbidity meters, and then you have to measure to get the values. At least you have to measure. You need the equipment, but for the head loss, it is nothing. Just observe the water levels. So in terms of the operations, so when we will have to do the backwash, so when we will have to do the backwash, we prefer the times to reach. We prefer the times to reach the total head loss first before it reach the breakthrough times. What does it mean? It means that we prefer the times to reach the head loss limit before the times to reach the breakthrough times. Because here, if we want to go for the backwashing process, the times when it reached the head loss limits should be before the times to reach the breakthrough times for the turbidities. So this is the head loss. This is the maximum head loss, maximum allowable head loss, and this one is the maximum okay, so this one is the maximum level for the turbidity, and this is the head loss. So we want this one. We want the head loss limit times to be reached first, because this one is observed. It's easy to observe. So if the water levels get maximum allowable limits, then we go for the backwash. But if this located below it, so if this happened before, what what is the problem? It's also not the problems, but you have to keep on measuring the turbidity. Okay, so in terms of the operations, we prefer the head loss limit to reach before the breakthrough times. Okay, if we just after backwash, so how the turbidities will look like. So if we clean it, uh, uh, if the bed, if the filter media it's perfectly clean, after operation, the turbidities will decrease. and can be used for a long time. So after backwash, so turbidity will decreased. Initially, it may be increased, but after operated for some times. Why during the initial times of the operations, the turbidities will increased? Because some of the dirt that accumulated may be coming out. But after some time, so all the dirt are washed out, the incoming liquids, the turbidities coming along with the incoming liquids will be accumulated in the between the pores. So all the turbidities will be accumulated. So in the effluents, you will never see the higher turbidities until it reached the capacity, so it gets increased again. So this one is 100% the backwashing, 100% perfectly clean it. Okay, but if we like a normally backwash would take like approximately 30 minutes for cleaning. So we put the waters in the opposite directions. We do it like approximately 30 minutes. And if we do only 15 minutes, what will happen? Some dirts are not, uh, some of the materials are not removed. So it's not 100% clean. So if it's not 100% clean, and if you use it again, it will not be a problem. Still, the turbidities will decrease and then gets the lowest points. This is 50% clean in terms of times or in terms of the volumes. It doesn't matter, but it's not 100% perfectly done. So if it's just only 50% clean, it's also not the problems. But the only thing is, if you operate it for some time, so it will reach the maximum capacities. For 50% clean, then after some times, the concentrations of the turbidities in the outlets will increase. So if you don't clean it perfectly, okay. So this is a kind of how we operate this uh, uh, filter just before uh, cleaning or backwashing. uh, I've got some hot news from the faculty members' lives. We have one master student got infection with the COVID-19. Luckily, he was actually he's my students. He's our students. Have been teaching the course that he is enrolling, but luckily we have never meet in persons. We only meet where a online system, like we have conducted the class, uh, like I have conducted a class with all of you. Okay, so this is a kind of how we operate the rapid science filters. The initial loss is about 0.5 to 0.8 meters. The backwash it's required when the head loss exceeds 2.5 to 3.3 meters. After backwashing, we can expect it around 50 to 20% expansion. So I mean, if we put the sands like after we filter the water, the sand. So if the depth is 50 centimeters, supposed to be 50 centimeters after backwashing, so the depths will expand a little bit, about 15 to 20%. Some of the dirt will be flushed out during a backwashing process. But the problem is the ideas of the backwashing is you have to wash the settling velocities of the media. Usually it's sands, or it could be a anthracite, it could be a gravel, whatever. You have to watch the settling velocities of the media. This is the settling velocities of the media. So backwashing rate. So this is the backwashing rate. Backwashing rate should be approximately or slightly greater than the settling velocities. Otherwise, there is no meaning. Okay. We backwash because we want this media moved. We want these media get moving a little bit so that or some abrasion occur so that the dots that get attached on these media will be washed out. So some abrasion we expected to occur. So in that case, we need to maintain the backwashing rate slightly greater than the settling velocities of this media. So if we use a small backwashing rate, the media doesn't move. So the cleaning will not be occur efficiently. So the settling velocities, upflow velocities must be slightly greater than the settling velocities of the sand grain. Only under this condition you can expect the full expansions of the bed. Okay, so this is how we performed the backwashing. This is a kind of a criteria. So somebody may ask like what should be our backwashing rate. It is much higher than the filtration rates. Backwash, you can do it two ways. Only water, backwash with only water, and surface wash auxiliary. We can apply solely water for backwashing if we only used one types of the medias in the filters or a single medias. If you only use the sands, you can use the water. But if we used dual media, for example, we put like a we use the anthracite and sand. So anthracite should be aligned above or below the sands. Anthracite นี่ควรจะอยู่บนหรืออยู่ล่างฮะ Anthracite นี่ควรจะอยู่บนหรืออยู่ล่าง
ควรอยู่บนนะครับอาจารย์
Why? Because I put it up there, up here, right? Anthracite, if you think about the densities, it is much lighter than the sands, right? So if you do the backwash, what will happen? After backwashing, you cannot maintain a higher backwashing rates because the settling velocities of the anthracite and the settling velocities of the sands are totally different. The backwashing velocities you can apply only you can only apply a greater than the settling velocities of the anthracite. Of course, it is much smaller as compared to the sands. So in this case, we need to blow the air. So if we want to backwash, to increase the efficiencies of the backwashing. So for the dual media, at least we need to blow the air. Backwash with the air auxiliary. Water backwashing is always required, but we have to blow the air along with the water, so that the air will help to remove the dirt attached on the surface. And after backwashing, so how does the water will look like? This is the wash through pipe. This is the wash through channels. This one, wash through channel, and all the dirts coming up along with the backwashed water and being accumulated or received by this wash through pipe. So as I told you initially, we have the wash through pipes in case of the rapid sand filters, but the wash through pipe or wash through channels are not used during the filtration, but it is used only when we backwash the media. Okay. Okay, so these are the details about the filtration. So we have okay, choice for backwashing. You can actually go through it by yourself. Any other things I need to emphasize? No more. Okay, so now we have already finished the 40 filtrations, which is one of the most important unit operations in water treatment plant, and we only have a few unit operations and unit processes left. So we can talk about this again next week. I hope next week we can complete this chapter. But anyway, in this afternoon, I will talk about the coordinations, which very close to the labs that we have to do it online this afternoon. So I will spend some time to finish this 4 or 5 slides so that we will not have to come back to talk about this again next week. We can skip this disinfection next week. Actually, this is one of the most important unit processes in water treatment plants, especially during this time, during the outbreak of this COVID-19 disease. Okay. Do you have any other question? มีคำถาม
อา
ไห
จาม รย์
ฮะ
ครับคาบบ่ายเราทำ lab ไหนนะครับมันไม่อาจารย์ไม่ได้โพสต์แบบเนื้อหา lab มาให้เลยครับ
coliform ไม่ได้มีเดี๋ยวผมอาจจะโพสต์ method ลงไปในช่วงพักเที่ยงนี่แหละนะฮะ coliform กับอะไรนะ biological examination นะฮะสาหร่ายนะครับ
อาจารย์ครับแล้วอย่างนี้เราจะอ่านควิซจากไหนครับ
จาก instruction ก็ได้ฮะจาก instruction มีเรื่อง coliform biological examination อะไรสักอย่างหนึ่งนะครับ
coliform เหรอครับอาจารย์
ใน instruction manual เพราะว่าจริงๆแล้วอันนี้ไม่มีอะไรไม่มี theory อะไร document อะไรนอกเหนือจาก method เท่านั้นเองเดี๋ยวประมาณช่วงพักกลางวันเดี๋ยวผมจะทยอยลงให้มี2 lab coliform กับอะไรนะmicrobial อะไรสักอย่างหนึ่งสาหร่ายนะฮะ algae investigation
ใน instruction เจอแต่ biological ครับ
มันมี2อัน1กับ2นะฮะ combine
โอเคครับอาจารย์
ครับโอเคครับงั้นเดี๋ยวเราเจอกันตอนบ่ายโมงครึ่งนะฮะเดี๋ยวพักรับประทานอาหารก่อนนะครับครับมีคำถามอื่นไหมฮะ Any other question